Let's get started. Um, so the take-home exam will be available at 10:30. If you go on Blackboard under content, there's a couple of things that you're going to need. This will be available, as you can see. You can't see it yet on your Blackboard, but it'll be there at 10:30. And so you'll be able to download a Word document version of it if it decides it wants to actually let me, enable editing. Okay, so sorry, let me zoom in here. Okay, so this is the format of it. It'll be available at 10:30. You may submit it to me one of two ways. You may print it out in class or by email. I've included my email by 9 o'clock on Monday. So you have from now until Monday to get it done. I highly recommend, and as you'll see, because we're going to walk through it here, I highly recommend doing it in stages because I've designed it that way. You're required to work on this assignment by yourself. You may not work with anybody else on this. The only source you are permitted are your class notes and homework submissions, the course textbook. You may use Blackboard and the TGOs and example questions, as well as the videos that I've posted on Blackboard. For whatever reason, if I find that you've cheated, meaning that I've determined that you've used some sort of external source, or I've determined that you worked with somebody else on this exam, you'll get an automatic 0. And since it's worth 20% of the final grade, I think it'll be impossible for you getting a grade higher than a C. You're permitted to type answers. The other key thing is if you scan it, I have to be able to read it. So if I can't read it, if you get an exam back and you do it like this and you see CR, if it actually decides to write CRCG, can't read, can't grade, for those of you who've had me before. If I have that on a take-home exam, that means I've showed it to at least a couple other professors, like, can you tell what this says? And if they say no, then, no points. But just use common sense on that. If there's any doubt, you are permitted to ask me questions, as I say right here. Honor code. So you're required to rewrite this honor code and sign it. For those of you, none of you have had me for a take-home. I'll just say you need to rewrite it, and I won't let you hand it in until you've done that. So I pledge my honor that I have not cheated, nor will I cheat on this exam. So the first part, so I've kind of phrased it as though you are preparing for a job interview and then actually doing a job interview. For step 1, I have found this is an actual solicitation on Intel's website for a currently existing job, meaning you could actually apply for this job right now. Especially if you're a graduating senior. It's their physical design engineer position at the platform engineering group in Folsom. Must have a minimum of BS degree in electrical engineering or computer engineering, computer science. That's you. Minimum 3 months experience in basic circuit functionality, behaviors, passive and active circuit structures. Minimum 3 months experience with complementary metal oxide semiconductor design, component design principles. Sound familiar? Basically, take my class. Minimum of 3 months experience with very large scale integrations component design principles. So this is a job where if after completing this course, you'd actually be able to be qualified for it. And once you graduate as well, I should also add that detail. So preferred qualifications, writing production software code using languages. You'll be able to do Unix operating system and CAD layout software, which you'll definitely have by the end of this course. So step 1, I'm actually going to have you guys write out a resume. So you want a job, you actually got to prepare for it. So on Blackboard, there's a sample resume. So if you go here, if you go to content, decides it wants to do it, and you go to professional. You'll see sample resume and power verbs. That sounds something like you see in Idiocracy or something like that. But this is a actual this format I used here is actually a format that was given to me by Intel's veterans group to help veterans be able to communicate better. The transition can be hard for veterans. So I've included my format. And what I want you to do is I want you to go through and format this resume as though you were applying for the job that's posted on the exam. So that's going to be the first, I think, 25 or 30 points or whatever I had. So design engineer is different in this case. On this case, you're applying for a physical design engineer. So you want to actually have the job reflect what it is. So you go through, look through the details, find what it is they're looking for, not just qualifications, but scheduling assignments independently to the right intermediate milestones. So you want to be able to say that given a project, you can meet milestones and do it independently. Solving complex design process problems, which you will do later in this exam. Basically, you want to hit on as much of this as possible. The key thing to remember is that the person who's going to be deciding whether or not you get to interview for the position is an HR person, and they are not qualified to do your position. So they are looking for keywords to pass audits. So ultimately, when you apply for a number of jobs once you graduate, you're going to have a number of resumes. Like George, I think George works with me in research. George already has 4 or 5 different resumes for 4 or 5 different positions. They have little minor tweaks. You want to make sure that your resume that you're submitting comes in. So the reason why I'm doing this is in order to obtain a job, the first thing you got to do is actually convey yourself properly. So follow these. Make sure you keep your resume around, because in the take-home exam 2, I'm going to have you modify it based on what we've covered since this exam. Yes, Josh.
So when we do this resume, you want it to be in that exact format?
I will. Yes. Let's see. Keep the same format, especially since it says detail oriented. So just read over this and I'll help you out. Yes.
Do we have a limit on the page number?
I would highly recommend keeping it below a page and a half. I mean, I don't even have 2 pages, and I've been around longer. So that's the first part. So then the second part is preparing for the interview. So congratulations, your resume impressed the Folsom Group and you received an interview offer. So then they'll do something like this. Obtain a copy of CMOS VLSI by Westy and Harris and review the basic concept. You'll be asked open-ended technical questions regarding your knowledge of CMOS component design principles and VLSI design principles. So you see in the job description, it said CMOS design principles and VLSI design principles, right? So I've phrased the question in the way that they may ask it. So in this section, you'll review basic questions, familiarize yourself with the greater concepts in step 3. So you can spread these out. So I've included 20 questions here. They'll probably look familiar if you go on Blackboard. So the whole goal of this is to review your notes, review the video, regain the familiarity. So this exam is supposed to actually mimic the job obtaining process. So you go through like, okay, these are the key things that I need to know. Right? Describe the physical layout of an N-type semiconductor. Describe the operation of NMOS and PMOS at the terminal level, all these different things. Parasitic delay, mobile integration. State the 4 values used to determine noise margins. Primary metrics for timing response of the CMOS device to its inputs. All of these things will look really familiar. So step 3, now you actually get to the interview. You've fully prepared, and you're going to have 6 additional questions here. Compare and contrast. Compare the operation of CMOS inverter or CMOS transistor gate at both the terminal and gate levels. Describe in detail how they work both physically and logically. Key thing is look at the keywords. Pick things out. I've phrased these questions, and to give you a hint, what I'm talking about, terminal and gate levels, I've phrased it that way for a reason. Especially once you review section 2, you'll understand what I'm getting at. Number 2, we know that this is the equation for a drain source current. how are these equations derived specifically? How does the channel charge, oxide thickness, permittivity, capacitance, the charge held by the transistor channel, and electric field contribute to the final equation? So 10 points, you have a problem here where you have an ideal NMOS transistor processed with a drawn channel length. That should look familiar to you. 4, an engineer has proposed the circuit to the left as a 4 transistor AND gate, which inputs the same value with the desired timing delay. Assuming that your beta values are the same and the threshold voltage for NMOS is equal to the absolute value of the PMOS, what will actually happen when the circuit operates in the region of operation? You got a similar question, and I gave you a hint. Consider the instance when it switches from A equals 1, B equals 0 to A equals 1, B equals 1. That'll help you out with all the different ranges. This one, identify the critical path. What's the minimum amount of slack, and how would you modify the circuit operation? And number 6, design the CMOS transistor for F equals not A, B, or C. Then draw a stick diagram. Draw the circuit with transistor widths to achieve effective rise and fall resistance to its unit inverter. Compute the rising and falling propagation delays. That'll look familiar once you review your questions. And so I have one last thing here. Grad students are required. Undergrads may earn up to 8% extra credit. This is 2 designs of a 2-input NOR gate. Prove which design is better. Hint, compute the rising and falling propagation delays of a 2-input NOR gate driving H-identical NOR gates using the Elmore delay model. So that is your exam. You have from today until Sunday to do it. And so that should be if you can do that, I could say rather confidently, if I were writing you a letter recommendation, that you could solve complex CMOS and VLSI design concepts. So when you do this, and last year when I gave a similar exam, I think the lowest score was an 87. So I think students ended up doing very well on it. So make sure you pace yourself. Don't wait until Sunday night. And the whole goal should be something where if you keep the resume and you keep your exam and you're preparing for job interviews, you should be in really good shape. Ultimately, the goal is to get you paid. So, on that note, does anybody have any questions before we start lecture? Yes, George.
As far as definitions go, do you want them like verbatim as you tell us how to teach you, or do you want them like in our own words?
If you're preparing, I would recommend. Oh, you mean for section 2? Section 2, I would recommend using them as presented in class. If I've given you the exact answers and I've allowed you open notes, might as well do that. They're like, here's the exact 100% right answer. Let me see if I can screw it up a little bit. All right. So we've talked about logical effort so far. In previous lecture, we talked about we had this example where we had one inverter driving a set of other inverters, right? So in this case, we had one inverter, and the logical effort is the ratio to the unit inverter, right? So it became 1, and it's driving 4 outputs, right? So we determined that electrical effort, and the parasitic delay of a unit inverter is 1. So we found the stage delay as 4 times 1 plus 1, which equals 5. And then we did the same thing with the ring oscillator, where we had some odd number of rings, right? And so we had calculated So we had to calculate the frequency. So the first thing we did was we calculated the stage delay, right? So here we have 1 times 1. Each one is driving 1, so it became 1 times 1 over 1 plus 1, which became 2. So in order to get from even to odd, right? So we had since we had frequency, we got to know the length. So the period is 2 of those. So each stage delay is 1 change. So in that case, 2 of them is going to be 2 changes. So that became 2n. And then it's changed twice to create a signal. So then we have to do the frequency. You have to do 1 over, right? So this would be 2. We multiply it by 2n to get 4n, and then from there we get the frequency. So logical effort of paths. So in this case, what happens when you have multiple gates along a path? So I'm going to scroll down really quick and show you this diagram. So what happens when you have a situation like this? We have some sort of output capacitance of 20, and we have an inverter, an NOR gate, a NAND gate, and an inverter, right? So we're trying to figure out the path logical effort and the path electrical effort in this case. So in order to actually figure that out, let's do some definitions first. So I should mention here that this is a mistake I see happen very often. Inexperienced designers often end up in the simulate and tweak loop involving minor changes and many fruitless simulations. So what ends up happening is they go, oh, I got to design this certain design. So they do this and they put it together and then they put it onto the next cell, expecting it to work. Oh, if I put this cell on this cell, it'll work, right? No, it will not. And we know why, because you have a lot of, you have to worry about this logical effort. You have to worry about how much it's going to actually take depending on how much signal you have in order to be able to design a circuit. So what ends up happening is designers, they get 2 cells that they think are going to work, right? And they tie them together like, oh, this is going to be great. And then suddenly the signal output sucks. And they have no idea why. This one worked, that one worked, what's wrong? You have to worry about this concept of logical effort and electrical effort. Because otherwise, if you're driving a number of these cells, the more that you add and the more you have downstream, it becomes problematic. So in order to do that, first we're going to define path logical effort. So each stage has its own logical effort, right? So those previous problems, we calculate the logical effort of an inverter tied to other inverters. So one case was tied to 4, the other case was just 1, and there was just a number of them tied together. So the path logical effort is the product of those projects along each stage. So G is the logical effort, and the product of those becomes the total logical effort. The other thing we need to worry about is the electrical effort of the whole path. It's given as the ratio of the output capacitance of the path to the input capacitance. So it can be given as the ratio of the output capacitance the path must drive divided by the input capacitance presented by the path. And then the path effort, so we have just like the effort is the logical effort times the electrical effort. So we had F equals G plus H before, right? Or G times H before. So now it's just the product of all of those. So the product is each one. So this just becomes Gi and H of I. So if you have an inverter, that's not the best inverter, and then you have some sort of OR gate, some sort of AND gate, right? I'll put an I there for inverter. You have some sort of output capacitance and input capacitance. So what you're doing is you're going to determine each one, right? And then you're going to multiply them all together. And then you're going to take H here, this path electrical effort, and then be able to calculate the full path effort. And that becomes important because that determines the sizes that you need in order to be able to actually design a particular path. So if you're doing a 32-bit ALU, right? So one of the worst case scenarios you can have in the MIPS ALU was going through the carry bit through the 32-bit adder, and then you have to go through a multiplexer and then to the output, right? So your output, if we had 4 bits on the input to control the ALU. So that means we had to have a 16-to-1 multiplexer, which means you actually had to go through 4 different, that consists of 4 different stages of 2-to-1 multiplexers, right? So you have to go through 32 adders and then 4 2-to-1 multiplexers and then your output. So in order to make sure that that signal has the same integrity as everything else, you have to worry about path effort. So in this case, here we have this circuit. So we have the pathological effort here. And what we're going to be doing is we have our logical efforts here and electrical efforts here. And so the reason why it's phrased this way, with 20 over z here, z over y, y over x, and x over 10, is because when you actually set these up in the way in which we have them in TGO 3.17, they're going to cancel out. So you can get 20 over z, z over y, y over x, and x over 10, right? So these all go away. And that's why we can say in 3.17 that's the ratio of the input to your output. This is your input to your output. Likewise, we're going to multiply these together. We have, remember, G is equal to the summation of G of I. So this becomes 1 times 4/3 times 5/3 times 1, which becomes 20 over 6. And the path electrical effort is, as I described just a second ago, you multiply these together because the effort, that electrical effort is the capacitance here over the output capacitance. So this ratio to this ratio is good, this to this, this to this, this to the input. So as a result, they actually will cancel out physically, and that's why we're able to do 3.17 in this manner. The C out is equal to C over Cn is the effort there. So then what's going to happen is, sorry, give me a split second to look that over. So this is 20 over 6 and 2 in this case. So that's the pathological effort and the pathological effort. So then continuing on in 3.9, 3.9 goes through here, right? So, I'm sorry. No, the 3.9 ends there because I think the question said give me the pathological effort and pathological effort. So 3.9 it did end here, sorry. So does everybody see why that makes, does that make sense to everybody? What's up, Trey?
How is G3 4 over 3?
That's given.
Oh, that's given.
Yeah.
Okay.
Yeah, these are given values. Yeah. Remember, this is, okay, so actually, it's actually, I probably should be a tad more clear. So this is an OR, and this is an AND, right? So why can I say this is 4 over 3 and this is 5 over 3? What did we discuss last lecture? Since you all still have your TGOs, which I know you did diligently, even though I didn't require them turned in.
From the table?
Yeah, from the table, right?
From the table that you gave.
Mm-hmm. So from previously, Demba is exactly correct. Remember we went through a good amount of time being able to prove the logical effort of common gates. So the NAND gate is a 2-input NAND gate, right? And then 2-input NOR gate. So in this case, in the inverter is 1. So we have 2 inverters, 1 NAND gate, and 1 NOR gate. So if let me page down here a little bit. So using our table, so yeah, does that make sense to everybody? And we're given an output capacitance of 20 and an input capacitance of 10.
So up in that chart with the electrical gate effort for the XOR and NOR, how do you know when to use, if you have like 8 and 16 or 1 6?
Depends on the number of inputs.
Well, no, like I do is 1 input, like 3 inputs.
Right. So you would, so then that would just be defined in the problem. I would say, okay, so if we had a 3 input XOR gate, right? And it would just define which input was which. It's more than likely going to be the middle one. It's going to be the highest one. So
Dr. Morrison,
yes.
Does G3 represent the NOR gate?
Yeah, it's 5/3 represents the NAND gate. Or yeah, it's. Oh, because it's this is 20/Z, so that's that one. Remember 20? Yeah, there you go. No. This is something. Okay, so this is a good point. No, you got to be able to understand why this is. So this is your path, your electrical effort, right? So it's 20/Z. So why does this definition represent? Yeah, path out or path in. So this is 20/Z, right? And so Z/Y is this. So Z/Y is your AND gate. Y/X. I don't know why that when they presented the solution it was that way, but and then X/10 is like that. All right, so we're accounting for fan out in multiple paths. So I remember we had these problems where we had, we created F equals not A plus B, and then we were driving a cell where one of them was driving the A input and the other one's driving the B input or C input. So you have to worry about these kinds of things. So here in this case, what happens is you have an output capacitance of 90, right? So this is 90/15, and so this is 15/5, right? So the H just becomes 90/5 in both cases, right? So here we have, all right. So 90/5 is 18, and then the stage is 1, because remember it's the sum law, so it's 1 times 1 equals 1. So here, this fan out, right, covers both 15 and 15 here, right? Because we have a fan out of 2, which means we are driving both this inverter and this inverter. So H1 is going to be 5 or 15 plus 15. Does that make sense, Josh? Okay. And that becomes 30/5, which becomes 6. And then H2 becomes 90/15. So we divide them into stages, right? So now we have 6 and 6. We have G1 and G2, which are both 1, right? So it's going to be 1 times 1 times 6 times 6, which is equal to 2GH. Right? Because we have a fan out of 2. It makes sense. So because of this, we need to worry about this concept of branching effort. See, if you just, up to this point, all the problems we've done have had a fan out of 1. So this output drives 1 gate. And we have another one here, just like the previous problem. Actually, the previous 3 problems. So what we're going to do is we now have to worry about this scenario. So we're going to worry about something called branching effort. Now, before we get into branching effort, does anybody have any questions on what we've done so far about path effort and path logical effort and path electrical effort? Okay. So in this case, the branching effort is the capacitance on the path plus your off the path capacitance divided by your path capacitance. So we define it as the ratio of the total capacitance seen by a stage to the capacitance on the path. I can scroll down a little bit, see? And then the path branching effort is the product of the branching efforts between stages. So you saw in that previous example, we kind of broke it up into stages there. So it kind of was alluding to these equations. And so because of this, we can now compute the delay of a multi-stage network. So this is important because pretty much any design you're going to do is going to obviously have multiple stages, and you may want to have multiple fan outs within those, right? So now you can actually calculate this out and allow this to do the proper sizing. So we have these instances where you path up. Oh, that was a little too big. This path effort delay, which is the sum of all your path efforts. You have your parasitic delay and your overall delay path. So we calculated this guy before, and now we're adding in parasitic delays, which we can calculate or are typically given in such problems. So 3.21, what this is basically saying is that if you have a set of stages and you've designed it such that the effort in each stage is the same effort, we define that as the best stage effort. That's equal to the multiplication of the logical effort times the electrical effort, and that's equal to the overall effort, that's 1 over n, right? So F is going to be your overall effort, and if you take log of n, right, that allows you to figure out your best stage effort, which is, so this is an ideal number. So you would adjust your input and output capacitances if you're trying to figure out this best stage effort. And then you can find the minimum delay by multiplying the number of stages times your best stage effort plus the parasitic delay of your device is equal to your minimum delay. And so that's why we call it best stage effort, because if it's not the best stage effort, that means you're going to have delays where each stage or stages are bearing different efforts. And as a result, that's going to slow you down. So this is why logical effort becomes important, right? So this allowed, the reason why Dr. Sutherland's concept becomes so important is because it allows us to know only the number of stages and path error and parasitic delays without needing to assign transistor sizes. So this allows you to have, if you're talking about your Gansky-Kahn chart, using logical effort, if you're designing from the gate level up, allows you to have an optimal design without having to worry about how those gates and transistor, why those gates and transistor sizes are. And its delay depends on sizes. Okay, so I'm sorry. So it's superior to simulation in this case because the delays are dependent on sizes and they never achieve certainty. You can never achieve certainty that the sizes selected are those that offer minimum delay. So the reason why this is important ties back into what I was saying at the beginning of lecture today. A lot of people waste a lot of time in CMOS by trying to do simulate, test, simulate, test, simulate, test. When I took CMOS, when I was a senior at USF, and we learned a lot of these concepts, I went through the design and came up with the logical effort of I did some Klein-Mikulski and then figured out the minimum path effort and then began designing the circuit. Whereas everybody else is like, okay, let's do NAND gate, let's put the NOR gate together, let's do all this. And then it didn't work and it kept not working. They couldn't figure out why. Well, it said so right in class that if you did that, it would fail. Whereas you can reduce a significant amount of your design time by figuring out logical effort of your circuit. And so how do you do that? GGO 3.23, and then we're going to do this example question that should show you precisely how it's done. So you work backwards. You have your logical effort and electrical effort, and that's equal to the ratio C out equals C in. And then if you solve it, we have our best path effort, the output capacitance, times the logical effort. So working backward, apply capacitance transformation to find the incapacitance on each gate given the load that it drives. And so how do we apply that? We have this circuit here where we have some two input NAND gates with an input capacitance of 8. We have two input ORs with a output capacitance of 45. And we have some sort of 3 input NAND gate network. So here in the previous problem we were just solving this part, right? Where we just had the one path, but each path branches. So we have a branch here and a branch there. So we actually have to worry about that in our circuit design to determine our minimum delay. So we have to estimate the minimum delay of the path from A to B in this figure. The initial NAND 2 may present a load of 8 lambda of the transistor width on the input, and the output load is equivalent to 45 lambda of the transistor width. So that's just relating it to the output capacitance. So then determine the gate sizes of X and Y. So the path, the first thing we do is we know the path goes from A to this 2 input NAND gate through this 3 input NAND gate to this 2 input NOR gate to the output. So we know that this is 4/3, right? Because it's 2 plus n over 3. And we know that this is going to be, this 2n plus 1 over 3, sorry. And this is going to be 2 plus n over 3, so this becomes 5/3 because it's 3 inputs, and this is 4/3. So it's going to be 4/3 times 5/3 times 5/3. This is going to become 100 over 27. The next thing we're going to do is we're going to do the electrical effort. So it's going to be 45 over y, times y over x, times x over 8. So this just becomes 45 over 8. And then the next thing we're going to do is calculate the branching effort. So here what we have is a fan out of 3. So it drives 1 gate, 2 gates, and 3 gates here, right? And then the next stage along this path, it goes 1, 2. So this is 3, and this is 2. So to determine our branching effort, we do 3 times 2, which is 6. So you have 100 over 27 for electrical effort. Our path electrical effort is going to be 45 over 8. And then our branching effort is 6, right? So what we're going to do next is just multiply all those together to get our path effort. So in this case, now you probably should start being able to tell that this is a designed problem to give simple solutions, because this comes out to 125. And then if you take, since it's 1, 2, 3 stages, right? If you take the log of 1/3, or the cube root, you're going to get 5, right? Also, we know from our table that we had 2, 3, and 2 for parasitic delay, so we can sum those. So it's 2, 3 input NAND gate and 2 input OR gate. So that becomes 2, 3, 2, and is 7. So we have the number of stages. If we go back to that previous equation where we get the minimum delay, it was the number of stages times your overall path effort to 1 over n. So remember, it was n times f 1 over n, right? Plus your parasitic delay. So we know n is 3. We calculated f to be 125 to 1/3, which becomes 5. Plus the parasitic delay is 2, 3, and 2 from the table, which becomes 7. So this becomes 15 and 7, which becomes 22. So that is the minimum delay of the circuit. And from there, that's when we start to do this whole working backwards thing. So now, we know the output capacitance. Since we're given these, we can actually figure out our sizes. So in this case, we start with, oh, hold on, let me scroll up so I can show you exactly what I'm doing. So we start with this output capacitance here, and we try to figure out this value of y. So we have 45, and we have this equation here. Y is equal to your path effort over the output capacitance divided by your logical effort. So we figured out that the best stage effort was 5, right? So now what we can do is go 45, it's going to be G. I'm sorry, so C out, divided by 5 over 3, because it's a 2-input NOR gate, right? Divided by 5, which is our best path effort. Those are going to cancel out, so that becomes 15. So the next stage, this input just happens to be this output. So now we have 15, and since that second stage there for for x happens to be the 3-input AND gate, we use our table. It's 2 plus n, which is the number of inputs, so it's 5 over 3. So these happen to be the same. Over 5, which is our best stage effort. So these cancel out, so this becomes should be 5. I don't know why it's 10. Typo. that make sense to everybody? So that's how you're able to calculate the sizes of your gates and how much the output capacitance should be without having to worry about the underlying logical effort. So from there, you could actually use these numbers and develop your transistor sizes. Does that make sense? Yes, no? People are fighting sleep. Week 5 of the semester. All right, so this is a very unique type of problem where we have to choose the best number of stages. You may just think, well, the best number of stages is 1, right? Well, it's not going to be the case because, as you recall, we have our equation where it's 1 over n plus p, right? So sometimes splitting it up into stages is beneficial. And we're going to learn this from a different set of inverters here. So there are different topologies that implement a particular logic function, right? So we have drivers, right? So we can kind of compare, do we want the inverted output? If we have this output as 4 inverters, this input has 2 inverters, and we have cases where they all have an output capacitance of 64, right? So what we're going to do, and the reason why we've chosen 64 is it has to drive each load, each bit slice of a 64-bit data path, as stated in example 3.11. So a control unit generates a signal from a unit-sized inverter. The signal must drive unit-sized loads at each bit slice of a 64-bit data path. The designer could add inverters to buffer the signal to drive the larger load. Assuming the polarity of the signal does not matter, which always does, but just the whole point of the problem is to see how logical effort and paths actually affect the circuit. What is the best number of inverters to add, and what delay can be achieved? For that number of inverters, determine the transistor sizes for each inverter. So how does this actually work? So for one inverter, we just have, so this is all of them put together, right? So in this case, let me change the color of the, okay. For the first one, G is equal to 1 because it's an inverter, right? And H is equal to 64. So our path effort is just going to be 1 times 64, right? So then this becomes stage if we have 1 times the first root of 64 plus n. So in this case, the reason we can say this, normally we would say plus p, but since it's an inverter, the parasitic delay is assumed to be 1. So this becomes 1 times 64 plus 1, which is 65. So in order to drive all of those, having one inverter there can be problematic. So what happens here is now we're going to figure this out at this stage. So we have the square root. We've broken into 2 stages now. So 2 times the square root of 64, so that becomes 8 times 2, which is 16, plus 2, which is 18. Three, so now we have 3 stages, so our parasitic delay is 3. So we put in n and n there. So this becomes 4 times 3, which is 12, plus the parasitic delay of 3, which is 15. So at this point, we're actually constantly improving, but you can see where we might have a problem because we continue to multiply this value every time. And so that 4-stage inverter, we have 4 times the 4th root plus 4. So that becomes 15.3. So because of this, we actually determined that the best is 15 here. So it becomes the 3-stage inverter. So for that number of inverters, determine the transistor sizes for each inverter. So then we just go through the same problem we did before. Logical effort is going to be is the product of all three of them, so it's 1 times 1 times 1. The electrical effort is the ratio of the output capacitance to the input capacitance, which is 64 over 1, which is 64. And our branching effort is just each stage just drives one inverter, right? So it's going to be 1 times 1 times 1. So since we have 3 stages, it's the cube root of 64 times 1, which is going to be 4. And then to determine the size for each inverter, we start at the end and work backwards. So we have 64 over 4 times 1, right? So this is inverter 3. So if we draw it out, we'd have inverter 3, and this is on 64, right? So 64 over 4, so that's a path effort, so this becomes 16. And then we have a second inverter here. So that's going to be 16 times 1 over 4, so that's going to be 4. So then you got 4 times 1 over 1, which is 1. So here we have 3 inverters, right? And sizes of 16, 4, and 1. But here's the interesting thing. If we had 1 inverter, we just have 64 and 1, and 1 on the output, right? And the best stage effort would be 1 here, right? So we just have this inverter driving everything. So it would be less efficient. So it would be a lot slower. In order to actually have this circuit work, you would have to make the circuit run a lot slower. So by having 3 inverters in this case, you could actually make the circuit run a lot faster. What do you mean inverter 1?
It's 4 times 1 over 1.
Oh, it should be 4, because F is this value. Does that make sense? Mike, you look like the computer's been reaching out and punching you. Oh, okay. So not the computer. It's whatever disease is infecting you. Okay. Okay. So so now we're gonna get to a much more complicated version of this. So we have ultimately what we have somebody who wants to design a 6-input AND gate. So how do you go about that? You could just design a 6-input AND gate like an A, or you can do 2 3-input AND gates and have 2 inverters and an AND gate on the output. You have 3 2-input AND gates, or you could design it like D. All of these are logically equivalent to a 6-input AND gate. So first, determine the minimum delay path for each design as a function of the electrical effort. Next, determine the minimum delay. So you're actually able to use this to determine which circuit this would be best. So here, I'm giving you a hint. So you see this 2-input AND gate with 2 inverters on it? So you would actually you would be adding more path effort by inverting this signal here. So instead what you can do is you can just make this a 2-input OR gate, some NOR gate, and it'll save you some logical effort. So for A, we have the number of inputs, which is 6 plus 2 over 3, gives us our electrical effort. Our path effort, times 1, which is your inverter. So that becomes 8 over 3. Your parasitic delay, if we go back to our table, it's 6 plus 1, so that's 7. The number of stages is 2. And so our best path effort becomes n, which is 2, times, this is n again, so that's 2 to the square root of 8 over 3 times h. We are given, and so if you look in the problem, the reason I did it this way is because at the end, next determine the minimum delay for h equals 5, 15, and 20, right? So what you can do is you can actually just create the equations and then do a table. And then you solve it out, and it becomes 4 over 2h over 3, because the square root of 4 becomes 2, plus 7, which is our parasitic delay. For B, what we have done is we have converted this to a 2-input NOR gate. So normally you would have to have another one and then an AND gate. Remember, an AND gate is actually an AND gate with an inverter on the front, right? So you'd have more stages. So here we've converted to a NOR gate that reduces the number of stages, so that is the NOR gate here. Then 3 plus 2 is our 3-input NAND gate. So that becomes 5/3 times 5/3 is 25 over 9. Parasitic delay is going to be 3 plus 2 for our 2-input NOR gate. So that becomes 5. So number of stages is 2 again. So this becomes 2 to the 2 times 25 over 9 times h plus 5. So that's 10/3 over the square root of h plus 5. So for C, we have 3 2-input NAND gates and 1 3-input gate converter on the outside here, right? So again, this circuit, if you use De Morgan's law, right? So in that case, what we can do is 3-input NOR plus a 2-input NAND gate. And since our parasitic delay is going to be 2 and 3, as we predict here, so it's going to be 4 over 3, which is 4/3. So it's because 6 plus 1 is 7 over 3. So that's 4/3 times 7/3, which becomes 28 over 9. Still 2 stages. So we have n over square root of to the nth root g times h plus the parasitic delay. So it becomes 28 over 9. So the square root of 1 over 9 becomes 1 over 3. So we bring the 3 out, so this becomes 4/3 over 7h plus 5. And then last but certainly not least, we do this 4th stage where we have 3 2-input NAND gates, inverters, 2 2-input NAND gates, and another inverter, right? So the path is going to go along 3, 1, 2, 1, right? So our 4 7s, this becomes 7 instead of 5 for our parasitic delay. Here, this is 3 plus 2 over 3 times 1 plus 2 plus 2 over 3 because there's a 2-input AND gate times 1 here. So this just becomes 5/3 times 4/3, which is 20 over 9. So you can see what happens. This effort comes down quite a bit when we're not using. See, these kind of higher relatively compared to these two. because we're only using AND gates and inverters. We're not using NOR gates. I'm sorry, NAND gates and inverters, not OR gates, NOR gates. And as a result, we have 4 stages. And so now we're taking the 4th root times 4 over 20 over 9 times H plus 7. And so doing some plug and chug, you could put those in a calculator, and you get the minimum path delays. So if you look at this table that we've come up with, for these two, for 1 and 20, 19.9 and 8.3 are the best. But if you look at H equals 5, D is the best. So depending on what kind of electrical effort you're using, you would actually have different designs. So I can scroll down here. You can see this table, and I put these equations in Wolfram Alpha. On the final, you'll be permitted to do the same, the equations you derive. So you can see how D kind of just levels off here. So at some points it's the best, and some points it's not. Whereas otherwise A is and the way that this graphed out, it starts at 5, not 0. So in case you're wondering, see it starts at 5. So at 5, it becomes the best. So you can see they're actually tied at 5.
And 20 is the best, correct?
Yeah, 20 is, well, 20 and A and D are, 20D is the best, yes. So you can see how D is kind of going out here. But over here, it's the worst. Okay, so we'll do this one last example problem, and I think we'll wrap up for the day, because it's also the end of section 3. All right, so number of stages affects the logical effort of the device, as you can probably think about, because it's the multiplication of each stage. And so here, this is one of the big problems in the textbook. This is a really good type problem to really combine all the concepts. So the memory designer for the Motorola, instead of motor oil for some reason, 6.8W86, an embedded automotive processor. The decoder is a 16-word register filled with a 32-bit word line. Each address, so now you're combining computer architecture with CMOS. Each address is used to compute half of the 16 word lines. Each bit presents a load of 3 unit size transistors. They are given a complementary address of A3 down to 0. Each input may drive up to 10 unit size transistors. Targeting a best stage effort of 4, determine the best number of stages for this device. So here we have 3 unit size transistors. So here's how you determine the first part. So it has 3 unit size transistors, and each address, the address consists of a 32-bit word line. So 32 times 3 is going to be 96. And so where the 16 regular word is going to come into this the branching. So what's going to happen is since each input may drive up to 10 unit size transistors, what's going to happen is your H value is going to be your C out over your C in, right? So this is going to be the ratio of 96 over 10. Right? Now what's happened is you have 16 word register filled lines, right? And the other portion is each address is used to compute half of the 16 word lines. So that means that each address is going to compute half of them, so you have 16 over 2, which is 8. And since you're driving inverters, G equals 1, this becomes GHB 9.1 times 9.6 times 8. So the way we figured this out, to go over again, we had 32-bit word lines, right, for each address. And each address is used to compute half of the 16 word lines. So additionally, each bit presents a load of 3 unit transistors. So you have an address that's driving 3 transistors, so it's 32 times 3, which is 96. And they're given, each input may drive 10 unit size transistors. So that input is going to be 96 over 10. And then to determine the branching effort, we know that we are calculating 16 word lines, and which is going to be half, right? So 16 over 2 is equal to 8. We multiply those together, we get 76.8. And so since the best stage effort is 4, we know that n is equal to log of n times your logical effort. So log of 4 of 768 is 3.1. So that means we're going to say that the number of stages is approximately 3. And then this circuit here is an example of a 3-stage design that actually accomplishes this goal. So here we have, for each line, we have the value in its invert. So it goes through here, goes through a 3-input AND gate, and on the output. So this is an example of a circuit that does this. So this is an example here. The reason why they're splitting up this way, this is an example of something known as dual rail. So a lot of circuits, they will have the value of the circuit and its inverse available at all times. And let me ask you guys this question. Why do you think that would be valuable, to have the circuit and its inverse's value happening at the same time? So if I get, for every value, I have a 1 or a 0 available in the circuit. What do you think is happening in those pull up and pull down networks? Enhance the signal, but what specifically about it?
Well, the ones that are activated in CMOS, the zeros activated the CMOS, and both of them are on at the same time.
Yep, in two different circuits, right? So that means I switch, and I'm activating the other ones, right? So what's happening is, now you're thinking this gains area, but what's going to happen is, if you track the power consumption, you have some sort of spike every time you switch. And if you're only switching PMOS and NMOS, especially if you have different logics in and or. We calculate they're all different. But if you're having a pull up and pull down, that means every time it's going to be very, very similar. And so what can happen, suppose if you have smart cards, the cards with pins, you can actually put the pins on there, get one of these oscilloscopes, and if it's poorly designed, you can use these difference in power spikes to obtain your cryptographic key and break into the person's car without having to deal with any of the software. And so if you do dual rail and you design it in such a way where you can actually minimize those spikes and make it prohibitively difficult. So this is how understanding the underlying CMOS can improve your computer architecture before you deal with one lick of software. Oh. On that note, does anybody have any questions before I dismiss you?
For the interview part of the test,
Mm-hmm.
are we like, for stuff to cater, the resume portion, when we're making our own resume,
Yeah.
are we using like actual?
You wanted to make it as though, consider it as though you're actually applying for this job, right? So you want to go back and see like, okay, well, what did I do in this specific course? What did I do in that specific course? Review the syllabus that I posted for this class, the kind of things that you would have. And you want to make sure that you convey, okay, I've taken this class. I have 3 months of CMOS, right? Or you will by the time you're done. That means I'm qualified for this friggin' job. Give it to me. Right? So you want to do it as though you're actually applying for the job. Any other questions? All right, then you all are dismissed.